Hello everyone. Welcome to this video on response surface methodology. In this video, I will briefly explain this methodology through an example. The response surface methodology, sometimes denoted by RSM, is a collection of statistical and mathematical techniques used to study and optimize a response that is affected by several controllable factors. Response surface methodology combines designs of experiments, regression modeling, ANOVA, model diagnostics, and optimization. It includes all those things. Usually, a first order model is used initially uh, when curvature is present. A second order polynomial model is fitted. Usually we fit a second order model like this. A general second order response surface model is given by an equation like this. So it has main effects. Suppose you are considering k variables, controllable variables. So then these terms represent the main effects, and then these represent the quadratic effects. And these are the products or sometimes called interaction effects. So usually we fit this kind of model using regression methods. And once we select that model as a reasonable model, that means by checking the model assumptions, goodness of it techniques and goodness of it technique measures and so on. Then we optimize that function to find out the minimum or the maximum. So optimization should be performed only after establishing that the fitted model is statistically adequate and that its assumptions are reasonably satisfied. So as I mentioned, I will be explaining this through an example. In example, we are considering one response variable and two uh, explanatory variables. An engineer wants to minimize the surface roughness, denoted by RA, of a mechanical component in a CNC turning process. CNC stands for Computer Numerical Control. CNC turning is a computer control machine process used mainly to produce cylindrical components. So here, two controllable factors or two controllable variables are studied. They are cutting speed. In short, we say speed. The other one is feed rate. In short, we say feed. So cutting speed in the experiment, cutting speed is set at several levels: 120, 100, 140, 91.7, 108.3, 48.3. The other one, feed, is also set at some fixed levels: 0.2, 0.15, 0.25, and 0.129 and 0.271. So these values are actually corresponding to some coded values, as I show you in a couple of slides. So the response variable is RA, that is the surface roughness. The objective is to determine the combination of cutting speed and feed rate that minimizes the expected surface roughness. So we want to minimize the expected surface roughness. So the experiment has carried out at using those levels of speed, those values of speed and feet, and these RA values have been observed. Notice here that, for example, this experimental condition, speed equal to 100, feet equal to 0.15 has been applied only once, right? We have only one observation corresponding to that treatment. And similarly, speed 100 and feed equal to 0.25, we have only one observation. Except it's like that for most observations, except for these observations where the same condition is repeated here. Speed is 120, feed is zero point 0.2. Right. For all others, you have only one observation for each experimental condition. But usually in this kind of experiments, uh, we use coded values for the variables. So this is called coding of the variables or coding of the factors. Actually, the variable, the name factor usually is used for categorical variables, but here they are not really categorical variables, but uh, distinct groups, distinct category. You can consider them category, but they have a numerical value. Coding places the factors on comparable scales. That is the main reason for coding, because sometimes, for example, here also the values, these speeds are in hundreds, speeds are in decimals. So those values are not comparable. And usually when you are fitting regression models with that kind of variables, with large differences in scales and values, there can be some technical problems. So this coding removes that kind of uh, large differences between the numeric magnitudes of the values. So they bring them to comparable scales. So here this capital X1 is speed is denoted by capital X1, feed is denoted by capital X2. They have been coded as simple X1 and simple X2. Here, what we are considering here is actually what we are doing here is the centered value, right? Here, for example, these factorial levels, these called the smallest or minimum level, is the maximum level. So center is 120 here. So when you are coding, you take away the center. And similarly, for the feed rate also, this is the minimum value, this is the maximum value. The center is this, right? So take away the center and divide by half the range. So here the range is 40. Therefore, we divide by 20, right? So take the mean away, mean middle value between the minimum and the maximum, not necessarily the mean, the middle value, divide by the half range. Here also the same. That's how they are usually coded in this case. Right. So when we apply that coding, we'll have four factor points, plus or minus one, plus or minus one, and for something called axial points like this, the values of x1, x2 values, right? So there are four possibilities here, and then four possibilities here, and then those replicated values at the same, in the middle, we have five of those values, right? So these will be the middle values. Five, we have five of those. So therefore, we can show this experimental design with respect to x1 and x2 in a picture like this, right? So if you consider x1 coordinates on this axis and x2 for simple x, simple x1 and simple x2. So this is the center. And then we have all the other experimental conditions, right? X1 is equal to 0, X2 is equal to negative zero point 0.5, right? X1 is equal to 0, X2 is equal to positive 1.5, and so on, right? So for each of these conditions, we have one experiment, and here we have at this level 0, 0. At that condition, we have 5 observations. So therefore, using simple X1, simple X2, I can now update my data set as this. So these are the ones that I will be using in the model, right, rather than these ones. So simple X1, simple X2, and array values will be used. So what we are interested in is actually, first of all, this second order response model. Two factors, the second order model is, for the two factors, the second order model is written like this, as I showed you earlier, right? The main effects, and then quadratic effect, and this is the interaction. Usually in this kind of response surface methodology, the hierarchy principle is followed. That means, uh, if, for example, quadratic or interaction terms are significant, we always keep the first order terms in the model, right? Statistically, they might not be significant, but still in that case, we keep them in the model. Uh, that is called the hierarchy principle, right? Once a higher order terms is in the model is significant, the lower order models are automatically kept in the model. Okay, so here I look at several models. First model, I consider the linear model. RA is the response. X1 is actually this, X1 is this column. X2 is the other column, right? So in this model, only the main effects are included, right? And then I also consider a model with interaction term without square term. So that means X1 and X2 term, product term is included. In addition to this, the product term is included. And also I consider the full model with the quadratic model, quadratic terms also. That is called second model, RSM second model. So here I put the coefficients in the second model in a vector called RSM coefficients. And let's look at the output of the second order model. Right. So this is the summary of the model. You can see that assuming that the model assumptions are satisfied at this level, at this moment, we can see that all the coefficients in the model are significant, very, very significant. And the R square value is very, very high. Okay. So therefore, we will consider this model, right? Because X square terms are significant. Because we are keeping the hierarchy, other terms have to be kept also, right? So therefore, we are not going to check whether we can drop, for example, the first order terms. In usual regression, we would do that, right? We will see whether some terms can be dropped so that we will have a parsimonious model. But in response surface methodology, usually we are not interested in doing that. So therefore, this is the fitted model. These coefficients have come from this fitted model here. These are the coefficients, fitted coefficients, or the estimated coefficients. Right. So if you look at this model, fitted model, the residual standard error is very, very low, and that's a good thing with this, for 7 degrees of freedom. Residual standard error is small, means overall error. It's a measure of the overall error in the predicted values. It's a small amount. R square value is very, very high. That you have to be careful usually in usually regression. This can happen, for example, if you have overfitted the model. But in this case, actually, it's because of a good fit. The overall regression is also highly significant. You can see that is not necessary actually at this point. Once all the parameters are significant, this is not a useful test, but it is also this the overall left test, testing whether all the coefficients simultaneously zero or not. Of course, obviously in this case, none of the coefficients are zero, so therefore it's a significant test. Right. But as I mentioned, these p-values will be meaningful and only if the model assumptions are satisfied. So therefore, we must check whether the model assumptions are satisfied. Right. So I have carried out the usual regression analysis. Right. In this case, we don't have that many data. We have only 13 data points. Right. But as usual, I have drawn the standardized residuals. Uh, Actually, here in this case, the studentized residuals versus the fitted values. There is no pattern. All the residuals except this one are within -2 and +2. So this probably requires some attention. But at the moment, I don't have any explanation about that observation. And then I have also plotted the residuals, studentized residuals versus each variable x1 and x2. So there is no pattern again. Here also there is no pattern. Notice that these points are actually those 5 points corresponding to the middle, right? Middle, the center, and then there are two other observations with the same x1, right? But there is no pattern here. So therefore, the model selected model seems adequate, a reasonable model. And also the normality. In order to test the normality of the residuals, I have looked at the normal QQ plot, and that indicates that all the points are very close to the reference line, and therefore it indicates that residuals are reasonably normally distributed. In addition to that, I have looked at the Cook's distance versus the observation order and also leverage values. Uh, the leverage value, all the leverage values are actually below the threshold because threshold is above this. Threshold is not mentioned here, I mean indicated here. So that means all these are okay. But here there are several observations whose Cook's distance is little large, larger than the reference level value here. But of course, just because uh, some Cook's distances of some observations are above or larger than the uh, reference or the threshold, we should not automatically remove those observations. Only thing I can say here is you have to be careful about those. It's better to go back and check whether there was any error, recording error, that kind of errors in those observations. As I mentioned, in this case, I don't have any other information about those values. Therefore, I will just keep those things um, as they are, assuming they are correct observations. Main reason is actually we don't have so many observations. So if I remove these about there are about 5 observations, then I am going to be left with only 8 observations, which will not be enough to fit a second order model like this. So therefore, I must keep them at this point. Right. So the diagnostic summary, the residual plot should be examined for systematic patterns, and actually we have done, and we have not seen any significant pattern here. Shapiro-Wilk test was also carried out in addition to the QQ plot, and we saw that p-value is 0.4. So therefore, that indicates, in addition to the QQ plot, it also this Shapiro-Wilk test also indicates that residuals are normally distributed. we can conclude that at zero point zero 0.05 level of significance. There is one possible outlier, as I mentioned, which is greater than 2. That is the observation 8. So we should probably, uh, the researchers should probably look at that observation, re-examine that. And then there were several uh, observations for which uh, Cook's distance was larger, right? There were 5 of those. As I mentioned, I'm just going to keep them at this point. No observations exceeded the leverage guideline HH greater than 2P over N. Right? All of the leverage values are uh, okay. Right. So for that quadratic response function, if I plot the contours of that response, this is what I get. Right? The contours are the levels where the response has the same height. So you can see that the response was 4.5, 4.3, 4.1 like this, decreasing. And then within this, you have the minimum value. And actually, this is the minimum value, right? So there are other circles here, but only few, some of them are shown here. And later on, we will show you that this is the minimum value at that point. Response is equal to 1.816. So we can roughly get the value from this graph also from x1 and x2 value. Right. Once you get the simple x1 and simple x2 value, then you can find out capital X1 and capital X2 value. Those are the actual values of the variables. But we can mathematically also find out, rather than getting the values from the graph, we can mathematically, because this point here cannot be found out using the graph. Here I have marked them after finding it mathematically, right? This point was marked here after finding mathematically. Right, so this is the surface, actual surface. Here also I have indicated the minimum point, but that was found marked only after mathematically finding the point. Right. So how do we find out mathematically the minimum? We already know. Usually, when you have a function of x1 and x2, we have to differentiate that with respect to x1 and x2 and equate to 0 and solve those two equations. That will give you a stationary point, of course. And then by uh, usual tests, you can decide whether it's a maximum at that point, stationary point, is a maximum or a minimum or a saddle point, right? So when you solve these first derivatives equal to 0, we get this solution x1 is equal to 0.872, x2 is equal to negative 762, right? So that only tells that this surface has a stationary point at x1, x2 point. Then, in order to check whether it's a minimum or a maximum or a saddle point, there are several criteria that you can use. Here, I'm using this particular technique called using the quadratic coefficient matrix. Quadratic coefficient matrix is coming from these coefficients in the fitted response, right? So these two values, 251 and 541, are going to be in the diagonal of this matrix, and this value here and this value are the same. That value is actually the half of the coefficient of the product term. So that matrix is called quadratic coefficient matrix. Right? And how do we check whether at this point whether we have a minimum or a maximum or saddle point? We look at the eigenvalues, right? If I calculate the eigenvalues of this matrix, they both are positive in this case. These are the eigenvalues of this matrix. Since both eigenvalues are positive, B is a positive definite matrix. It's a positive definite matrix. So if B is, that is the quadratic coefficient matrix, is a positive definite matrix, then that indicates that this stationary point is a minimum. Right. So therefore, we established that what we have here is actually a minimum. From the graphs also, it was already clear. But if you don't draw the graphs, for example, this is how you establish that it's a minimum. Right. So you can now convert back to the original uh, variables. So capital X1, according to that, is equal to this number. X2 will be equal to this number. So you just convert back. Thus, the recommended operating condition is approximately given by cutting speed is equal to this number value, feed rate is equal to this value. That is where at those values we have the expected uh, roughness, the minimum expected roughness. Right. So predicted minimum roughness at that point can be obtained by putting x1 equal to whatever that value that we had and x2, those two values. And so in that case, we get RA hat is equal to 1.816. So that is the minimum value. From this graph also, we can see that's decreasing. So this is the point where x1 is that value that we found out, x2 value is the value we found out. And at that point, RA hat will be equal to 1.816. So at the center point, the mean surface roughness is approximately 2.2. That is what we had in our observations, right? So that is the minimum that we had. But fitting the response surface, we found out a better answer, right? That was not the minimum condition, right? So we found out the actual minimum, better x1, x2 value for a even a smaller, right? At that point, we have not taken observations because we didn't know that that was the minimum point. So what we had was some specific values, but using those values, you were able to find out minimum would occur at a different point. So that point is now established. Right. So once a minimum point is established through the response surface methodology, usually the engineers carry out experiment at those x1, x2 values to see whether actually the response uh, at those x1, x2 values is at least very close to the predicted value from the model. Right. So a confirmation experiment should be conducted at the recommended settings. So in this case, these are the recommended settings where the minimum would occur. So this is the predicted value. And when the experiment was carried out again, this was the observed value in that case. So you can see that they are pretty close. So the observed value is close to the predicted value and provides initial support for fitted response surface. The corresponding 95% prediction interval is approximately given by this one. That was calculated by the computer separately, right? There are these when we fit these kind of models, they automatically calculate these things. So that means we are 95% confident that the minimum minimum what is this RA value will be between these two values. Right? Replicated confirmation runs would provide strong evidence concerning the practical performance on the recommended settings. So here I have only I have only one observed value. So if you carry out several experiments at this condition, then you can also see how variable the minimum value would be in those experiments. Right. Uh, so as a summary of this response surface methodology, I have a few points here. A rotatable central composite design was used in this case. The design that we used is called rotatable central composite design. was used to estimate the second order response surface. Right? It's not me actually, the researchers of this research paper had done it. The interaction and quadratic terms are statistically significant, therefore curvature must be improved. Right. The lack of fit test, actually we didn't do it. I have not shown it here, but I carried out something called lack of fit test, and it was also significant that showing that fit was good. That is not a must actually. I mean, once you have this kind of high R square value and seeing that all the coefficients are significant and residual analysis shows that the assumptions are reasonable, this is not a must. But of course, in this case, we can carry out this lack of fit test because we have several observations in the middle. Right? If we didn't have those observations in the middle, a lack of fit test would not be possible. Residual and influence diagnosis should be examined before using the model for optimization. Right? So that's what we did. We first established that the model was reasonable. As a model, it's reasonable, right? And also, fitted model is suitable because the residual analysis didn't have any problem. So therefore, and then finally deciding that is a reasonable model, we use that to get the minimum point. The stationary point is a minimum because the quadratic coefficient matrix is positive definite in this case. So the recommended settings are approximately 137.4 for cutting speed and 0.162 for the feed rate with predicted surface roughness at that point is 1.82 units. Right. So that is actually the end of this example. Here I have prepared a table also. Now, as I mentioned, response surface methodology is actually a combination of regression, ANOVA, and all those model diagnostics and everything. So, what are the roles of these different techniques inside this example? For example, in this particular example, let's summarize those, right? So, we use ANOVA to find out which effects are significant. In this case, we found out that all the effects, right? Main effects, quadratic effects, and interaction effects were significant. That was found out using ANOVA, analysis of variance. So the role was test whether the speed, feed, interaction, curvature are important, right? The regression was used to build the prediction equation, right? Build the model. Right? It gives an equation for predicting RA from speed and feed. So that is the purpose, that is the role of regression. And then finally, actually, the response surface methodology is the part that optimizes the fitted model, right? Finds the best combination of speed and feed to minimize RA. So therefore, this whole problem is a combination of all those things. So that is the end of this video. I have also prepared a video explaining some of the misunderstandings and errors I saw in research papers in which regression analysis has been used. So I will present that part in the next video.